Thank you for kind introduction. First of all, I would like to thank organizers to giving me this opportunity to talk about my recent research. I'm using a high-speed AFM technique for studying ion channels structure and intermolecular interaction. Today, I will show you an example of application for the ion channel study of this microscope, especially on the voltage-gated sodium channels. So the PowerPoint doesn't work, sorry. Sorry. So I think this atomic force microscope is not so popular for this symposium. So I would like to explain the basic system of this microscope. The atomic force microscope is one of the scanning probe microscope technique, and the AFM uses a cantilever with a sharp tip like this, and this cantilever senses the distance between the sample surface and the tip surface by using the laser beam and the photodetector like this. Then by using the AFM, we can observe this sample surface structure of this sample in solution in room temperature. That means the near physiological condition, in buffer solution or something. And the AFM, giving a high spatial resolution such as that is actually strongly depend on the sample situation. But in the best case for the membrane protein imaging, the horizontal resolution is about 1 nanometer, and the vertical resolution is about 1 angstrom. And if we use high-speed type of AFM, we can get 10 frames per second imaging in the best case for a biological imaging. So I have used this technique for more than 10 years, something to see the structure of ion channels. And here I'm showing you gating coupled clustering and dispersion of dispersion behavior of the proton-gated potassium channel. They formed a cluster in closed conformation like this, and they become dispersed mode when they open in acidic condition like this. And also here you can see two potassium channels interacting with each other in a reconstituted membrane like this by using high-speed type of AFM. And here is a toxin binding event onto the extracellular surface of the two potassium channels. Now binding and then dissociated. So we applied scorpion toxin into the buffer solution and captured like this movie. And we could analyze the binding dynamics using this movie. And here is from a different group, but they captured tetrameric structure and the pentameric structure of TRPV3 channel in reconstituted membrane. And here, I observed the thermal fluctuation of TLPV1 channel in reconstituted membrane and found that the molecular fluctuation is fluctuation depends on the ligand binding in this case. So I mean that the high-speed AFM can visualize the nanoscale, the structural dynamics of ion channel, and their intermolecular interaction like this. So today I will talk about a voltage-gated sodium channel. So since the physiological function of voltage-gated channels are very crucial, so there are many structural analyses. For example, X-ray crystallographic structure and cryo-EM analysis. And here is cryo-EM. Here is from cryo-EM paper showed the resting and activated state of the voltage-gated sodium channel with a side view. As you can see here, they have a power module at the center of the channel, and the voltage sensor domains surround the power module. And in popular opinion, the voltage sensor domains always attaching the power module regardless of the gating state. However, on the other hand, there is a molecular dynamics simulation of the voltage-gated potassium channel. This paper showed that in the resting state of the channel, voltage sensor domains dissociated from the power module in resting state. So our first question is to clarify the voltage sensor domains always attached to the power module or not by high-speed FM. And the second question is about the cooperativity between voltage-gated sodium channels. Here is experimental data of the action potential from neuronal cell, and the second panel showing the simulated action potential waveform with a Hodgkin-Huxley model. So you can see at the steep rising phase of the action potential between these panels is not so completely matched. So, however, if they include the cooperative activation between the voltage-gated sodium channel, they got very clear fit to the experimental waveform. So this paper means the cooperative activation between sodium channels is important for the rise, especially on the rising phase of the action potential. And interestingly, another paper showed that strong positive cooperativity in about 10% of sodium channels reproduces action potential features. So, and also there is experimental result that in caudomyocyte, two sodium channels gate with strong coupling with 43 protein, and and here is a structural model with the two sodium channel and the adhesive 14-3 protein like this. But we don't know is there direct interaction between two sodium channels, and we don't know the molecular detail of interchannel interaction. To address these issues, so we use high-speed FM and sodium channel. In this case, in this experiment, we use bacterial sodium channel NAV-AB as a model of voltage-gated sodium channel. And here is a schematic illustration of structure. And they form a tetrameric structure of this protein, and we attach the hexahistidine tag at the end of the polar domain. And to see the different gating state by AFM, we use several mutations in the voltage sensor domains to change the voltage dependency. And we successfully shift the voltage dependency like this. And the wild type, for wild type channel, this channel is always the activation gate is always open at 0 millivolt, but this double mutant is resting state. And to see the surface structure of the sodium channel, we put this purified channel onto the AFM substrate via nickel histidine interaction at the end of the pore domain. And we apply the lipid molecules to form a lipid barrier like this, and see the extracellular surface structure by high-speed AFM. Here I'm showing the result of wild type channel. Here you can see 4 bright particles. These are corresponding to the 4 particles of the pore domains. And we can see smaller particles surrounding the pore module, like this. And this result is very similar to the previous structure, previously reported structure. And in the single mutant, having an intermediate voltage dependency, showed a very similar structure to the wild type, but several voltage sensors are missing in this mutant. And in the resting mutant, we found that voltage sensor domains dissociated from the pore domain, so we cannot see the attaching voltage sensor domains just around the pore domains, but they dissociated a little bit far away the pore domain, like this. So here is a schematic illustration of the result. So by using a high-speed AFM, we found that the voltage sensor domains dissociated from the pore in the only in the resting state. And here we analyzed the trajectory of each pore and the pores and the voltage sensor domains like this. These are trajectories. And we analyzed coupled motion of each domain. This PC analysis, principal component analysis. This result means the vectors, ball and stick indicates the vectors of only coupled motions. So in the wild type channel, all of pore domains and the voltage sensor domains are coupled, especially in the rotational motion. But in the intermediate mutant and the resting mutant showed only pore domains are coupled each other, but voltage sensor domains are not coupled anymore. So this result means inter-protein interaction between pore domain and the voltage sensor domains are changed by gating state. And here is a discussion for this result. Our high-speed AFM result is very similar to the result reported by MD simulation, molecular dynamics simulation of potassium channel. And here is a paper that describing that investigating distance between the end of a pore domain and the voltage sensor domain. This paper reported that during activation of the channel, each end is attaching at the open state, but in the resting state, this distance between these positions are very far, more than 20 angstrom. They discussed mainly in the about the up and down motion of the S4 helix like this, but this result is not contradictory for our result. And finally, about the cryo-EM structure or the voltage-gated sodium channel, they reported that the voltage sensor domains are always attached to the Bohr domain, but actually they use the cross-linking between the Bohr domain and the voltage sensor domains. So we think if they don't use the cross-linking between the Bohr domain and the voltage sensor domain, the voltage sensor domain might be dissociated from the Bohr domain. And additionally, we found unique structure in the high-speed AFM image. The particles are like this, and the structure is very similar to the dimerized structure of voltage sensor domains. And actually, the voltage-gated proton channel, which consists only of the voltage sensor domains, forms dimer in vivo. So we assumed that the dissociated voltage sensor domains in resting state can form dimers in the membrane. To verify our hypothesis, we carried out a molecular dynamics simulation with homology modeling of the voltage sensor dimers like this, and the dimeric structure of voltage sensor domains are stable at least for 1 microsecond. And using this result, we calculated AFM image by using the MD simulation result, and the simulated AFM image is very similar to the actual experimental image. So we concluded these 4 particles correspond to the voltage sensor dimers. Next, I would like to discuss whether the voltage sensor dimers can form in physical density of channel. So you know that at the node of Lambier, there are many sodium channels like this. The density is about 1500 channels per square micron. And also, in recent super resolution microscope, revealed that the organization of the sodium channels in the node of Lambier is like a striped shape, like this. This means the local density should be significantly higher than this density. And if we put the circles having about the diameter of 20 nanometers, indicating the resting channel, with a random distribution in square micron area with this density, the result is like this. So you can see the many circles are overlapping in this random distribution. And we calculated the contact probability between channels, between circles from this image, and also the smaller circle indicating the open conformation. And we found that in this situation, in this random distribution situation, about 84% of resting channel can interact with each with another channel at the density of this channel density. And interestingly, about 12% of resting channels can interact with 4 other channels at this density. This is reminiscent to day harvest. If about 10% of voltage-gated sodium channels has strong positive cooperativity, they could reproduce its action potential features well. So as summary, we we propose this cooperative gating mechanism of voltage-gated sodium channels. In the resting state, the voltage sensor domains are detached from pore domains and form interchannel dimers like this. And at the density of 50-100 channels per square micron or something, they form interchannel network like this. And when channel opens, the voltage sensor dimers dissociate and open the channel upon activation. We think this is a possible molecular basis for the cooperative activation of sodium channels. So finally, I would like to thank especially for main collaborators, Takashi Mikihiro Katsumasa for this paper, and also these people for sharing laboratory instrument, technical assistance, and also this fruitful discussion. Thank you for your attention.
Thank you very much for nice talk. Dr. Sumino, please. Yeah.
Thank you for beautiful presentation. Upon activation, upon depolarization, does the S4 domain in the dissociated state move up, or do the upward movement occur only after associated with the pore domain?
Actually, I cannot answer that question clearly.
How about your speculation?
Speculation. Probably the up and down motion of the S4 hair is much faster than the dissociation. The attaching the voltage sensor domains to the pore domain. But this is my speculation.
What you mean is, as the S4 movement is faster, so then moves up first and then associate with the pore domain at a depolarized state.
I think.
Okay.
I think. But we need further evaluation with a longer MD simulation or something. Thank you.
Yeah, I have a question. If this cooperativity is important for activation of the NAV, probably you can test the following experiment. You could co-express full-length protein with some truncated protein or some mutant with reduced activity of voltage sensor domain. Could influence not just the summation of each protein, but some cooperative depletion or reduction.
By some electrophysiological
method. Actually, I have done experiment with co-expression full length and truncated NAV in Zenpath oocyte, and we found some dominant negative effect. We didn't publish, but so I'm really interested in your idea of the cooperativity.
Okay, thank you. I will check the paper. Thank you.
Any question? Please.
Thank you, Professor Sumino. I always love a bit of voltage sensor domain structure function studies, so very pleased to see this. This might be trying to crack a nut with a sledgehammer versus some of the very, nice and subtle and nuanced studies that you've done. But would you be able to get any more information on these states and the dimerization through concatenation? So you almost force the channel into a certain dimeric state through concatenated subunits. Would that help at all, or do you think that might just be too forceful a way of studying such dimerization?
Sorry, I couldn't follow your question. So could you?
It's quite confused, to be honest, because I'm obviously quite confused. I'm almost suggesting that would you be able to get more information by forcing this dimeric format through concatenating.
Yeah. Yes, we can examine such experiment by changing the design of the channel or something.
Okay.
Oh.
Thank you. I might need to try and catch you afterwards and even figure out what I'm asking you.
Sorry.
Okay, please join me in thanking Dr. Sumino for nice talk. Let's move on to the next speaker.